So what did we do last time? Okay, so last time we did sort of a contact intro / survey, sort of about like how these things work now, for the most part, like a few different options and like pros and cons of all these things. And then we got into solving simulation problems with impacts in this like variational mechanics, discrete mechanics sort of framework. And I would argue this is like the most natural, most like theoretically rigorous way to do this. It's that least action problem again. You just slap inequality constraints on it for interpenetration, turn the crank, and you get like impacts. And it's very clean and very nice. And basically avoids all of the like issues, both numerical and sort of like physics artifact sort of quirks that you get with all the other methods. Okay, so today we're going to continue that story and talk about friction, specifically Coulomb friction, which is sometimes called dry friction. And it's sort of the friction you get between two solid objects when you try to like slide them against each other, right? Which is also super nasty and non-smooth. We'll talk a little bit about that. So we're going to talk about how we pose this also as an optimization problem to capture the non-smoothness. And that optimization problem is called the maximum dissipation principle. Has anyone heard of this or seen this before? One or two of you? Yeah, this is surprisingly recent. This guy Moreau, French dude, like did this stuff like, I don't know, 1970s maybe is when this like the theory of this was kind of like done. It's like, considering how old mechanics as a subject is in general, like the rigorous like mathematical like variational treatment of Coulomb friction wasn't done until the 1970s. And actually simulation methods that could do this and reproduce these things weren't really invented until like the 90s, which is kind of crazy. There are a bunch of weird paradox things that happen with Coulomb friction. They're pretty wild. Maybe you've seen, I can't do it here, unfortunately, because we don't have chalkboards anymore, but there's this one, that famous one. There's this thing called the Penn-LaVey paradox. Should definitely do the YouTube video for this. At the end, we'll do the YouTube video. So it turns out if you take like a piece of chalk and hold it at an angle to the chalkboard, so like this kind of idea, and push really hard and go like this, it skips and it'll draw dashed lines. Anyone seen this before? So yeah, this is pretty nuts. And it's actually this thing called the Penn-LaVey paradox. There's this weird mathematical paradox that shows up in the equations for Coulomb friction in basically this circumstance. And it turns out the way the paradox gets resolved, like the way the math sort of works, is that the chalk has to actually leave the surface. And so like what happens is if you do this and push real hard and slide, it'll actually hop. And that's like how the math, like if you write the math out for like sliding friction in this case, it does weird stuff and blows up. And the like physical resolution of the paradox is that the chalk jumps off the board. It's pretty wild. Okay. I get excited about these things. Anyway.
Does Coulomb friction have anything to do with like the unit of measurement of Coulomb?
No. Same dude, obviously. But yeah, I don't think so. These are separate ideas. Okay, and then the last thing we're going to talk about is the most common so-called time stepping methods that are used in simulators. So this is what Bullet does, Dart does, like Gazebo stuff. These are called LCP methods. Super common. You have almost certainly, if you've used a robotic simulator like Gazebo, whatever, you've used these before. These are what those things are doing under the hood. And these are basically a bunch of like linearization simplifications on top of what we're talking about. So you take all the variational stuff we're doing, this maximum dissipation stuff, you go into those equations, which are nonlinear and kind of hard to solve and slow. You make a bunch of approximations and linearize some stuff, and you get these LCP methods, which are kind of the standard thing in a lot of simulators. So I'll show you where those come from. Okay, cool. So let's do the Coulomb friction story. Okay, so last time we talked about non-smooth impacts. And if you try to write these down in some kind of F equals MA thing, way, bad things happen, right? We get all kinds of like very stiff ODEs, all kinds of badness. And we kind of saw that if you formulate this as a constrained optimization problem with inequality constraints, like nice things happen, and it works pretty well. And we're going to kind of basically latch on to this more general idea that if you have a non-smooth thing, it often can be formulated as some kind of optimization problem with an inequality constraint. So this is what we did last time, right? So we wrote down our least action stuff, and we wrote this sign distance, interpenetration constraint that says thing is not allowed to penetrate through the ground or whatever. And we saw how when we write down the KKT conditions for this constrained problem, like all the nice things that you expect to happen physically kind of pop out of those KKT conditions, right? In particular, the so-called complementarity conditions and the KKT conditions that encode like active set switching and the constraints end up encoding all of the like physical things you expect about impacts, right? Like no force at a distance, everything has to be positive, forces can only push, et cetera, just kind of fall out of like standard optimization theory, right? Oh yeah, we'll recap those. So we got these guys, which were our kind of discrete Euler-Lagrange things. So this looks, pretty much exactly the same as any other kind of thing we've done. This looks exactly the same as any other, equality constrained problem where we have a constraint with a multiplier where the n is the multiplier here. But we get these extra KKT condition things associated with the inequality constraint, right? So this is constraint has to be positive, aka no penetration. Multiplier has to be positive, aka forces can only push. And then we get this complementarity thing, aka no force at a distance, right? So we did that on Tuesday. Cool. So now we're going to look at this Coulomb friction stuff, and I'm going to draw some pictures kind of like last time at the beginning to sort of illustrate the non-smooth stuff that happens. And the non-smooth stuff here is associated really with qualitatively with stick-slip behavior. And this is like a really basic fundamental thing, right? Like if I take, I don't know, the one I always like to do is if I take like let's take this eraser and like sit it here, right? If I tilt this, actually this is very slippery, so it's not super good demo. Let's grab something else. Let's grab this guy. Like if I take this and tilt it, right? Like it doesn't move. And if I kind of keep tilting it maybe more and more, at some point I've static friction and the thing slides, right? But there's sort of, so there you could think about it as some like critical angle where we'll slip at this, but before that it doesn't move, right? It doesn't creep, it doesn't slip at all. And then there's this like transition point where all of a sudden it starts to slide, right? So let's try to kind of like draw this, and vice versa, right? If I like push this thing on some plane, I could do this experiment here, right? Like it stops at some point, right? It doesn't keep sliding forever. At some point, there's this transition between slipping and sticking, right? Either direction. So let's draw that. We'll draw that version where I started out sliding and then I let it kind of come to a rest, right? So if I think about what that looks like in like, if I plot like V versus T, say, or X dot versus T, I'm going to get something that's, sliding. So something like this, right? Speed's decreasing until it sticks and then it is stationary, right? So like this, and this curve has a kink in it, right? So let's write it down. So we call this part slip and this part sticking. if I now think about the accelerations or forces on this guy, plot the next derivative. This is weird, the auto snap thing. I get something that looks like, say, this is t, this is x double dot. I'm getting, during the slip phase, there's friction force pushing on me, right? And it turns out with Coulomb friction, that's basically constant. And it looks something like this maybe. And then all of a sudden, I get this transition to sticking. Right, so I was moving, and then I stop. And like similar kind of non-smooth transition. Okay, so that's sort of like position acceleration. Basically, we get this jump discontinuity flavored stuff happening, kind of like last time. Let's think about what the forces look like on this thing. This is pretty weird. So if I push on this thing, there's some friction force. Like I can push on this with some force here, right? There's some friction force that's opposing the motion while it's sticking. Now I'm asked the question, what is this, the force? What's the friction force? What's the friction force right now? It's probably about 0, right? And it's not moving. If I push a little bit, it's non-zero, but it's still not moving, right? So if I tried to write down friction force as a function of velocity, it's actually pretty weird and doesn't make a lot of sense. Let's think about this for a sec. So here's like, let's say friction, which we're going to use B for friction. So this is like a 2D vector in general, right? And then this is like x dot, the velocity. So if I try to write this down, so like, you know, a lot of times we think about things like viscous damping, where if you wrote down like a damped simple harmonic oscillator, friction would be, or damping force, right, would be a linear function of x dot, right? You get like something proportional to velocity, right? Here, what this Coulomb friction thing looks like is something like this. I get, if I'm sliding, I get a friction force that opposes the sliding motion, right? But if I'm in the stick, it's basically looks like this. So if I'm sliding, you know, to the right, I get a friction force that's opposing that motion. To the left, I'm sliding, you know, to the left, I get a force opposing that to the right. What happens in the middle though? This is sticking, right, along this axis. It can be anything in here, right? It's whatever it needs to be to oppose the applied force, basically, but it's not a well-defined function of velocity, unlike viscous damping, right? This is a pretty weird thing. So this is the sliding stuff. And then like during the sticking phase, we don't really know, just from looking at velocity, you know, whatever, I can't tell you what the friction force is during the sticking phase. We have to like look at some other stuff, and it's very weird. So this picture in the 1D case, you may have seen this in like, you know, a fresh physics class, kind of written like this, right? Where you've got some friction coefficient mu times the normal force. We say, you know, so it doesn't depend on the velocity at all, right? It just depends on the applied normal force. If I'm sliding, this is during sliding, and then you can actually write it in the 1D case, you can write it like this. Right, so this is this plot, right? So this is the signum function, right? Sine of x. This is like opposing velocity, and it's just proportional to normal force. So this would be, you know, normal force. So everyone's seen something like this before, right? Friction coefficient. Okay, so yeah, the issue is if I try to like go simulate something with this, this is super gross. And it doesn't actually, if I have a brick sitting on the table and I push on it, like this doesn't actually tell me what the friction force should be until I start sliding, right? There's this like ill-defined section here. And so how do we reason about that? How do we like actually compute forces in that situation and blah, blah, blah. Okay, so here's how you do it. This is basically a special case that only works when you're already sliding, right? So the way we do it in general is this maximum dissipation principle thing.
Sorry, Zach, what's a B?
B is the
that
friction.
The friction force.
Yeah, exactly.
Thanks.
Yeah, let me label that too. Thank you. Okay, so we're gonna like sort of generalize that, you know, freshman physics thing to 3D and sort of to the case where we're not sliding. And so a couple things about this. Smooth contact models. So one option here would be to take this guy. This is a non-smooth equation, right? Quite obviously, it does this weird switchy thing. This dumbest thing I could do, the simplest thing, which is what more or less what the soft contact simulators do, like Mujoko, et cetera. What they'll basically do is take that sigma function and approximate it with like a tangent or something, in which case you smooth this guy out. And now it has something in the middle that like has some slope to it. And you can actually write this down, et cetera, et cetera. And it looks like some weird nonlinear version of damping in the middle, and then sort of asymptotically approaches the Coulomb friction answer as you slide. So that's one option, but those will produce creep, right? Because in the middle, it has some slope, and it'll no matter what, if you like did the chalk on the inclined plane thing, it's always going to slip a little bit, right? Because there's no kind of like, to get stick, you need this sort of discontinuity, right? This sharp discontinuity there. So let's write that down. Smooth contact models, like Mujoko, always have creep. And this is like the naive thing you would do, right? You would take that signum thing, approximate it with some smooth like sigmoid function, tangent function, whatever. Yeah, this is another, I guess this is like, you know, the sorts of things neural network people do also a lot. Okay, so to model like true Coulomb friction, we solve another optimization problem. And this is pretty intuitive. I'll write it down, then we can talk through it. So we're going to solve this thing. And I'll explain what all this is in a sec. Okay, so this thing is the time derivative of kinetic energy. Which we call, you know, dissipation. So dissipation, the idea of dissipation is like, you know, when this guy's negative and I'm sucking kinetic energy out of the system, right? So what this optimization problem says is the true friction force, B here, is the one that instantaneously sucks out the most kinetic energy from the system, which makes sense, right? Like that's what friction does, sucks out kinetic energy, dissipates energy, subject to this constraint, which is called the friction cone, which I'll draw a picture of in a sec. So this says, you know, norm of B has to be less than or equal to mu times the normal force. So this is like generalizing that guy from like freshman physics, right? To like arbitrary 3D stuff. And the nice thing is, right, so what this is doing now, this is basically getting you the stick slip behavior. When we're not slipping, when we're sticking, B is less than or equal to mu. We're inside the cone. And what happens is you can imagine now if I'm pushing on the chalk eraser or whatever, like I was doing there, right? I can push, push, push. It'll produce whatever B is necessary to get rid of all the kinetic energy, right? So when I push, 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 if B is inside the cone, this holds like inequality style. Then that's saying that I can produce as much friction as I need to keep the kinetic energy at zero, right? To keep me at rest. When I get slipping is when I push up to the boundary here and I can't have any more friction, and this holds with equality, then I don't have any more friction to give. So now I start having a non-zero kinetic energy. I start slipping. That makes sense? So that's like the physical interpretation of this guy. And like what's kind of going on intuitively. Hopefully this makes some sense. So we'll draw the picture. So we've got, you know, if I imagine the ground or whatever, my surface, and my contact point here, I have this kind of deal. This cone, and then I've got my normal force. And no, so for a given normal force, that's this side, right? I have to stay, you know, less than or equal to here. So this defines this cone. So this would be like, oops. So hopefully that makes sense. That's like just the picture is what that constraint says, right? Okay, questions about this? Who's heard of friction cone before? This comes up quite a bit. So this is where it comes from, and this is like what's actually happening, right? And that nicely encodes all this stick slip stuff. So this is basically the right thing at this sort of like stick slip interface. Friction in general gets more complicated than this, but it gets more complicated once you're sliding. Right, so you've probably heard of, you know, like in freshman physics, you talked about like static versus kinetic friction or whatever. And there, you know, kind of what we say is the mu changes, right, at this transition maybe. So in general, it's more complicated than that. There's like Strybeck effect and all this other weird stuff that happens. It's super nonlinear, but all that is happening while it's sliding. So basically what that's saying is this curve up here, this is right to first order. So this Coulomb friction stuff captures this region of the curve really well. What's going on is with all those other effects, dynamic friction, et cetera, this is not a line out here. It does some iffy stuff and weird stuff once you're sliding. For us in this case, we're going to just, this is the picture that I just showed you, right? But you can add those other effects on top of this. Then what you get is you just get a function of velocity added to this, right? That can add those other effects. Okay, cool. That's the friction story. Friction in general is super nasty. But this captures really well the stick slip transition stuff, which is kind of the meat of qualitatively what we need, right, to get this stuff right. Okay, and yeah, the message is if you don't do it this way, if you try to do any kind of smooth thing, you're always going to get creep. You can never get true sticking, you know, static friction. Okay, cool. So now let's talk about this T dot thing a little bit more and like how you calculate that or what that actually looks like. So if I wrote down kinetic energy, that's just, you know, like 1/2 mv squared, or it kind of in a slightly more general fashion looks like this, right? We talked about this when we wrote down the Lagrangians. We get our mass matrix in here, which in general is a function of Q, blah, 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 this kind of thing. So if I just kind of diff this with respect to time, I'm going to get something that looks like partial T partial Q dot times Q double dot plus, you know, if I just product roll this, I'm going to get something that looks like partial T partial Q Q dot, which is sort of this, you know, this guy's derivative, right? Okay, so here's kind of where this gets nice. What am I minimizing this with respect to? B, right? The friction force. Does that show up in here anywhere? It shows up in the dynamics, right? It's a force, F equals ma, blah, blah, blah. So that shows up in here. It shows up in the dynamics, which is this Q double dot guy. B does not show up in this term at all. So that term drops out of the problem. Okay, and if I write this down, like, you know, kind of in more detail, this is just, looks like basically like a Q dot transpose M of Q double dot, right? Does that make sense? So I take this guy, I diff it with respect to Q dot, I get like, you know, Q dot transpose M, and then I multiply by Q double dot. That's what that is, right? Okay, so then the next kind of thing is that this is just the dynamics, right? So I just plug the dynamics in, and remember, I only care about the dependence on B. So everything else can drop out. So this simplifies down a lot. I guess we didn't talk about this yet in super detail, but you guys hopefully have seen this before. We'll do more of this next week. So I can write down like my manipulator dynamics that look like this. And if you have seen this, great. I think you guys do this in KDC, right? You guys, everyone's seen this before? Yeah. we'll talk more about this next week. But this is kind of what you get, right? So this is mass matrix, blah, 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 Coriolis stuff, gravity stuff. This is the Jacobian that maps friction forces into generalized coordinates or joint space or whatever you want to call it. So we'll write that down.
I think it was in that previous section.
Yeah, we've definitely talked about this stuff before. I just want to make sure. If anyone has, any, okay, so then what I'm going to do is solve this guy for Q double dot. And again, I only care about the B term, right? That's all I'm minimizing with respect to. So all the other stuff when I minimize is going to drop out. It's going to be constants, right? So then all I care about is this part, M inverse J transpose B, right? And I'm going to go plug this back in to the optimization problem. I'm going to get min over B, Q dot transpose M. Oh, the M's cancel out, right? Because I got M up there, and then I get M inverse here. So it just looks like this. Q dot transpose J transpose, which is a function of Q, B. That's it. So what is this actually saying? So this guy maps the friction force into Q space, into like generalized coordinates, joint coordinates, whatever. And this is my joint space velocity, right? So what is this actually telling me? It's the component of the friction lined up with the velocity, right? Which is like basically work that the friction's doing, right? Okay, and then the other kind of point is from an optimization perspective, this is a linear objective, right? Because I'm minimizing over B. This is generally some weirdo nonlinear function of Q and Q dot, but I don't care. I do this at a single time instant where I know what these guys are. I'm just evaluating the forces for the dynamics, right? So I only am minimizing over B, so it's linear in B, which is really nice and easy. And then I've got my friction cone step again. Okay, does anyone know what kind of optimization problem this is? So I have a linear objective function and a cone constraint. Is it convex? What do we think? Yeah, second order cone program, that's right, which is a convex optimization problem. Cones are convex, right? The rule for convexity is the line, pick any 2 points in the set, a line connecting those points has to stay in the set, right? So if you kind of like think about this for a sec, that's definitely true of a cone. All cones are convex. So that's great, convex set. And then linear objective functions are also convex, it turns out, right? So this whole thing's a convex optimization problem. It's a specific kind of convex optimization problem called a second order cone program. There's different kinds of cones, mathematically speaking. This, which is like the normal cone you kind of know from normal, everyday, not weird math land. This is called the second order cone. It's called the second order cone because it's a quadratic function. That's where the second order part comes in. You can write down other cones, like technically in math land, pyramids and weird things like that are also cones, mathematically speaking. Fun fact, but this one, the normal one that you're familiar with in the everyday life and call a cone is this one, the second order cone. And so the message there is this is a convex problem, and it's one in particular that we actually have really good solvers for. It's very nice, very easy to solve. So this is good. Yeah, also as a aside, program in math means optimization problem. It's an old word for like an optimization problem. So you'll hear linear program, right? Quadratic program. second order cone program, nonlinear program, blah, blah, blah. These are all program means optimization problem. Okay, cool. So that's that. Oh yeah, okay. So some more stuff on this. Okay, so this is all continuous time. What do you think we're going to do now? You discretize this in the usual way. There's actually like two ways you can discretize this. You can sort of, so here we're basically doing optimizing and then discretize. You can also like, you can kind of go optimize, then discretize, or discretize and optimize and get two slightly different flavors of this. At the end, it basically works out the same, but we're just going to like take this and discretize it in the usual way, like we've kind of been doing with everything. So we're literally just going to finite diff approximate the Q dot, right? That's basically it. So we end up with like min over B sub K over a time step where the Q dot becomes QK plus 1 minus QK over H. This is like J evaluated at QK. And then this is BK, the friction over the next time step, right? Subject to friction cone. So that's pretty easy. Now we're going to write down KKT conditions for this guy. So what does this look like? So I'll just write them down. This is easy to do though. Like what all you're doing is you're going to take that friction cone thing, you're going to move everything over to one side. So it's like less than or equal to 0, stick it in there with a Lagrange multiplier, take the gradient, write down the complementarity step, right? That's what we're doing. So not hard. So I get J times the velocity. Right? This is gradient with respect to B, right? And then the constraint looks like this. This is a one-dimensional constraint, right? So there's a scalar Lagrange multiplier. So it's lambda K. And then this looks like, when I take the derivative of the norm, that looks like this. dk over norm dk. Right? Does anyone know how to get this? Derivative of norm equals like 1 over norm, whatever. This comes from, I write down the norm as like square root of B transpose B, and I diff that, right? So that's pretty straightforward. So this guy equals 0. Then I get the same stuff we kind of were doing last time, the rest of the KKT stuff. So that looks like this. So that's primal feasibility, right? Dual feasibility. And then complementarity. Okay, now let's look at, this is Lagrange multiplier. Now we're gonna like talk about what do these things all mean physically. Okay, so what direction does B away? Okay, so first question is, what is the Lagrange multiplier here? Not the friction. Let's think about this. Okay, so what's this guy? The unit vector that points in the direction of friction, right? So it's friction unit vector. What's this guy? This is, yeah, so this is the like joint space tangential velocity kind of thing, right? It's the tangential velocity at the contact point, right? This is like the joint space velocity. This maps you back into like the end effector or whatever, the foot, you know, whatever you like, the contact point, tangent plane, right? Okay, so this is the tangential velocity at the contact point. This is the unit vector associated with friction. So this is just, you know, has a direction, no magnitude. What does this guy have to be? Exactly. So this takes on the magnitude of the velocity in the tangential velocity at the contact point. Cool. Okay. And then what does this say? Okay, so this basically what this is going to do, this thing takes on the norm of this guy, norm of the tangential velocity. So now what does this say about this guy for this all to work out? What direction does B have to point? the minus velocity direction. Does that make sense, everybody? Tangential velocity, unit vector. This thing has norm of tangential velocity, and this has to be positive, remember, right? So this has the magnitude, and then this guy, just to make the signs work out and everything be equal 0, this guy has to point in the opposite direction. So that gets you like the physical kind of, friction always opposes velocity thing. That's pretty cool. So let's write this stuff down, I guess. And then B always okay. Does that make sense to everybody? That kind of clear? What about this guy? What does this say? Can we interpret the complementarity slackness physically? It says one or the other has to be 0, right? Okay, so what does it say about, so this says, what does this guy say right here? When is this term 0? On the cone boundary, right? Okay, so this says when I have non-zero tangential velocity, i.e. when I'm sliding, I'm stuck up against the cone boundary, which checks out, right? When I'm slipping, my friction vector is pinned up against the boundary of the cone. When I'm not slipping, this guy's 0, and then this guy can be non-zero, aka sticking when I'm in the interior of the cone, and this guy doesn't have to hold the equality, right? Does that make sense? So that encodes stick-slip behavior right there. Sweet. Okay, excellent. So there's a couple of quirks I want to point out. This is totally legit. This is the exact answer, blah, blah, blah. But if I wrote these KKT conditions down just like this and tried to solve them, which we're going to do in a second, you can't really do it numerically. Does anyone know what's nasty about this numerically? What happens in the stationary case, or when friction is 0? If I'm that shock right there sitting down, what happens in that case? I get this guy blows up, right? Or I get a 0/0 singularity, which is mathematically, strictly speaking, fine. Like L'Hopital's rule, limit, blah, blah, blah. This thing is well behaved, actually, but numerically, this is bad. I'm going to get like some nasty divide by 0-y stuff. And really where that's coming from is the fact that the cone is pointy at the bottom. So there's like a non-smooth pointy thing happening at the bottom of the cone. That causes us numerical problems if we do this in a naive way. But the right way to do this, as we said last time, is to use a primal dual interior point method. If you do the standard conic primal dual interior point method, aka use a second order cone solver for this, it's totally good. You can just write this down as up here with the cone constraint, and natively it solves this and it deals with that, no problem. Okay, so there's a cautionary note about like naively solving this. You should use a legit interior point solver that knows how to solve cones. But we're going to use a stupid hack right now because I don't want to teach you how interior point methods work, because that's a whole several weeks of stuff. But if you're curious, you can look up SOCP solvers and primal dual interior point methods for those. And they basically handle this. It's not exactly the same as what we talked about last time, but basically what they end up doing is like having effectively like a slack thing in there that relaxes everything that you crank down as you iterate in the solver, and eventually crank down to like machine precision, right, to get the real answer. Yeah, so if you want to do this for real, go read up on these guys and like do it properly, or just use a conic solver. But we're going to do the dumb hacky version. So we're going to basically smooth the point at the bottom of the cone by smoothing the 2 norm. So we're going to change, so norm B, I'm going to write a smooth version of this that looks like the following. So exactly this guy is that, right? We're going to add a little epsilon inside here, epsilon squared inside, and then subtract it off on the outside. So what that's doing is when I add the epsilon squared inside the square root, it actually lifts the whole thing up and biases it up. But when this is 0, I get square root epsilon squared, which equals epsilon. So I'm just going to subtract that off. And that's lowers the whole thing back down to the origin, right? So I'm not like biasing things. And we're going to set epsilon equal to like some small constant. Here, we're going to use like 10 to the minus 6. So basically, what all this is doing is like rounding the tip at the bottom of the cone slightly, of the order like 10 to the minus 6. So it's pretty tiny from a physical perspective. If you're using like, MKS units of meters and stuff, this is stuff that's happening at like the, micrometer per second level or whatever. So it's very small. This is just to make the numerics work out. And really what it's doing is like, yeah, so we'll draw the picture. It does basically this sort of thing, rounds the bottom a little bit. That's what we're doing. And like the reason we do this is if we go plug this into IPOpt, which we're going to do now, IPOpt does not handle second order cones natively. It expects everything to be smooth. So this just lets IPOpt converge reasonably. And again, it converges to tolerances on that order, right? Like we're only perturbing at 10 to the minus 6. So it's actually like not a big deal. Yeah, basically, we're also going to use the same like complementary relaxation tricks we talked about last time for the impact part of this. Which again is basically a hacky dumb version of what a primal dual interior point method does under the hood. And if you really do it for real, you should do the right version. And then basically we take this stuff. So these KKT conditions with the relaxation tricks we just talked about, and we just stack those on top of the impact stuff that we did last time, right? So like literally this whole maximum dissipation optimization problem gets stacked with the least action plus impact optimization problem, and they get solved jointly, right? And what we're going to be solving for is QK plus 1, NK, and BK, right? We're going to solve for next pose or state, normal force, friction force, and the associated multipliers, right? But we're basically just stacking all these conditions and solving them all together. So now we're going to do it. Oh, yeah. Okay. Where is this code? Cool. Code that should work because I ran it last time. That's all right. This should also not be horribly slow because I didn't like restart this thing or whatever. Okay, cool. Okay, so blah, blah, blah. This is exactly the same like falling particle thing from last time. I just added friction to it. So same stuff, gravity, mass 1, 20 hertz, second and a half, blah, blah, blah. Initial conditions, same as last time. So I'm giving it like basically 3 meters up and then like a 1 meter per second velocity in the x direction, right, in 2D. Sine distance function, again, just spits out like the z height. So it's just the second element of the q vector, and the Jacobian is just 0, 1 for that guy. Discrete Lagrangian stuff, same stuff we've been doing all along. So we've got like, you know, mv squared, mgh, energy stuff, discretize that guy, take the derivatives. Cool. Discrete Euler Lagrange equations, same exact stuff. Oh, okay. So this is the version from last time right now with just the normal force. This is boilerplate IPOP code that is long and stupid. This is the constraints from last time. This is all this is from last time. So refresher. This is not the new stuff. And then we can plot all this stuff, right? Cool. And yep, keep sliding, right? Hits the ground, keep sliding, normal force, big spike, and then it's mg, all that good stuff. And then we converge, you know, 1e-6 type tolerances. Cool. Here we go. So now we're gonna do the friction version. So this is all the same. Now though, I've got the friction force in the x direction, normal force in the y direction, right? In general, you know, there's a Jacobian in here mapping these things, but in the particle case in 2D, this is really dumb and simple, so I can just write it explicitly like that. Here's my smooth square root function or whatever that I'm using to smooth that norm out. It's exactly what we just talked about with epsilon. I use 1e-6 because that's actually the solver tolerance in IPOPs is 1e-6, so that kind of checks out. Here's the meat. So discrete Euler Lagrange equation, maximum dissipation, KKT conditions, right? So this is the gradient equals 0 stuff, friction cone, relaxed complementarity for everything, right? And I'm just sticking in the smooth square root stuff for the norm, right, everywhere. Cool. So it's literally just everything stacked up like we talked about. Okay, now we're going to go solve this with IPOP. Nothing changed really. I just have a slightly bigger problem. Boom. Okay, so let's look at the plots. So here's now, this is the x. Remember last time it hits the ground somewhere around here. And now, instead of sliding forever, where this guy just keeps going, now what happens, I get friction in there and this guy sort of ends up zeroing out, right? This is the vertical component, right? So falls, hits the ground, cool. Normal force, exactly the same as last time, right? Big spike at impact and then mg. Here now this is the friction. So it's 0 while I'm in the air. I hit the ground, and when I have the impact spike in the normal force, because the normal force is big, I can also have a big friction, right? Because it's mu n. So I get a really big friction spike at the impact instant. But then after that, it gets a lot smaller. Like here, it's mu times mg, right? So here the friction is whatever, mu times mg. And then here is where I end up sticking, right? So the friction actually drops off. So here it's pegged to the boundary of the cone, right? And then when I start to slow down and stop, it goes inside the cone, and then like it's 0 when I'm stationary, right? That's kind of what's going on there. Here's a fun one. This is the Lagrange multiplier, tangential velocity. So what is this doing? It's kind of weird. So this kind of spikes up to the correct value at impact. And then here's the tangential velocity as I slide and sort of, this is the plot we drew right at the beginning over here, right? So this is impact, it's big spike guy. Then it slides down here until I hit 0, where I get this kink and it's stationary, right? So this all checks out. What's happening when I'm in the air? I don't have any thoughts on that. This is pretty weird. Yeah, so it kind of can. And actually what's going on here with this wiggly garbage, these are basically artifacts of the smoothing that we did. Those conditions are kind of funky and weird when you're in the air because n equals 0. Anyway, yeah, basically, oh, and then yeah, you can see we converge to basically 1e-6, which is cool. That's consistent with everything we did. So this is basically numerical garbage that's coming from the smoothing tricks. Otherwise, there's some like divide by 0 kind of weirdness that happens in the air that's nasty, right? Literally what's going on there, when I'm in the air, what happens to the friction cone? Remember, it's B, norm B less than equal to mu n. So when I'm in the air, n is 0. So what is going on?
B is really small and right.
Well, where am I in the cone? I'm pegged at the point of the cone, right? So everything should be 0, but what did I do to the cone? I rounded it out and with the smoothing trick. So literally this is basically the garbage that's coming out of the smoothing trick, where I should be pegged to 0 at the bottom of the cone, but this is what's happening because of the smoothing, right? And if I didn't have that in there, the solver would barge. So we had to do it, but this is kind of the artifact of that smoothing. Okay, fun facts. Any questions about this? You want me to try anything else? What did I make the friction coefficient? Let's try it. Let's mess with that. Fun. Mu, 0.1, that's pretty small. What should I do? Should I make it bigger? What happens if I make it like 1? 1 is roughly what like rubber on concrete looks like a tire on a car, or like a, a shoe on solid asphalt or whatever. So that's pretty, let's see what that does. This probably is just going to peg, right to, yeah. So this just like, because I've, at that instant of, it doesn't slide at all. It just kind of pegs right to 0. Get a big spike in the friction and then it's 0. I think that's why I set it to 0.1, because it was like, if I set it really tiny, right, you'll get a lot of sliding. You get the idea. Okay. Yeah, make it tiny. Run that again. Get some more slidey stuff. Oh yeah, and here's tons of garbage while I'm in the air, right? And then, 0. Cool. So here we get a lot of sliding. So I made it tinier, right? So this all kind of checks out. Big spike, mg, and then here, little spike, relatively speaking, and then I get friction that's mu mg, right? And then here, oh, I didn't plot this one. Yeah, so here, right, this is my tangential velocity, right? So I got a little spike around impact event, and then, lots of slidey stuff. And this, if I ran this out for a long time, would, kind of eventually stop, but you get the idea. Cool. Okay, code will be posted. You can play around with it. You can do the, 3D version for homework. Hopefully this helps. Cool. Okay, so what else is there to say? Get rid of this, I guess.
Hey, Zach.
Yeah.
So in the objective that you're solving in that, if you were to solve this with a second order cone program, would you just be adding together the objectives of the
Yeah, this is a good question. So this is kind of gnarly. We'll actually get into this right now. So basically the second order cone program is just the friction problem. The impact problem is in general a nonlinear problem, right? Because the objective may be kind of nice and quadratic or whatever, but the contact geometry is nasty in general. And that can easily be a non-convex nonlinear problem. So what you really need to solve this is an NLP solver that supports second order cones natively, which don't really exist. The only one that I know of is ours. Our Altro stuff can do this, but like really there aren't any good NLP solvers that natively support second order cones. So this is partly why people in general do the things I'm about to show you and approximate all this stuff. So let's talk through that and then we can revisit this in a sec. Okay, so yeah, I guess the short answer is you really shouldn't be doing that like, throwing all the things in the objective kind of stuff. It sort of doesn't work out super well in general. And I'm playing like hacky games here that are sort of not recommended in general. Yeah.
About the first condition, could you avoid all of those numerical issues? Just multiply the first condition by the normal thing with PK?
Yeah. So then what you get is so there is a sort of thing along the lines of what you're saying that does kind of work out. Basically, what you can do is square everything. So I can write down the cone constraint in terms of like B transpose B equals mu squared m squared. I could do that, right? I could square the whole constraint and it still works, right? It turns out numerically that sucks. Do you know why? It's subtle. It's not obvious at all. So I wouldn't expect you to get this, but it's very subtle. And I tried this back in the day and was like, what the hell? And that took me a long time to figure out why this sucked. And here's why it sucks. So this thing is a conic constraint. It's convex, right? It turns out the squared version of the constraint is non-convex. and the solvers just don't do well on it. So you really want to use this version. Even if you have to smooth the cone a little bit, the smooth cone is still convex, right? The squared version of that constraint is non-convex and makes solvers very unhappy, it turns out. There's a sort of obvious way to see that. So here we got mu n minus norm b. This is convex because it says stay inside the cone. If I square this, I get this guy squared minus, b transpose b. So it's quadratic squared thing, quadratic squared thing, right? Okay. What's the condition for convexity if you have a quadratic function? Yeah, so math-wise, what does that say about the Hessian? Positive definite Hessian. Okay. I have stuff squared minus other stuff squared. What's the Hessian look like for that thing? It's got, it's this part of the Hessian's positive, this part's negative. So the Hessian right there, just from looking at that, this guy has an indefinite Hessian with positive and negative eigenvalues. So when I square this, it turns out what you get is a saddle point problem, right? And it turns out this is very bad. Numerically speaking, like this version is great and convex. The squared version of that constraint, which is basically kind of what you're talking about doing, ends up being indefinite saddle pointy stuff in the constraints, non-smooth, or it's smooth now, but it's non-convex. And it turns out that's just strictly worse than having a slightly smoothed convex version. And again, the right thing to do is to use an interior point method to do this correctly and not the hacky stupid thing I did. But yeah, that's why you don't do that kind of thing. Okay, so cool. We did example stuff. Okay, so now I will tell you what people actually do in practice most of the time, and like how basically all the simulators, Dart, Bullet, gazebo things do this. So they basically are doing what we just did, but they approximate a bunch of stuff for computational reasons, some of which, maybe make sense, some of which, nah, you don't really need to do that anymore. So these are LCP methods, which you'll hear a lot about. Okay, cool. So roughly speaking, the methods we just derived are nice. They do really good things. They like do real friction, real impacts, no artifacts, whatever. But they tend to be computationally expensive. I would say grain of salt. Like if you actually tried, you could make this very fast, and we've done that. We've like written custom solvers that can attack these directly with like interior point stuff, conic stuff, whatever. You can make this go fast, but it takes a lot of work. So I don't necessarily agree with this statement, but this is what I would say robotics people in general would say. So most current simulators basically all the current simulators that aren't Mujoko. Mujoko does the smooth thing like we talked about. All the ones that do hard contact do this stuff that I'm about to show you. So this would be Bullet, Dart, etc. Make some additional approximations. Okay, so the first one they do, and you will know how I feel about this immediately after I say it, is they tend to use Euler integration. In fact, they all do. Which, if you take nothing else from this course, you should take away Euler integration is bad, and you should not do it. They do a particular flavor of Euler integration that's a little funky, and I'll write it down the way they do it, which is kind of in terms of a manipulator equation, which is maybe the easiest way to see this. So they kind of write the manipulator equation down like this. And this kind of shows you structurally what's happening. Okay, so there's manipulator stuff. Literally, I just plug in my finite diff velocity, right? Cool. And then I write down, oops. This kind of thing. And then maybe my, so that J transpose F would be, you know, all the contact stuff. And then also your control inputs or whatever. Cool. So this guy has all the contact stuff in it. Okay, so I write this down. This is like the dynamics part. And then I also write down sort of the kinematic part, which is QK plus 1 equals QK plus H times VK plus 1. Okay, so I kind of stack all this up as written. So I already know QK and VK, right? That's my current state. So I plug in QK here, QK, VK. Basically, I can evaluate all of these terms except for F, right? Which I'm going to solve for. And here I know this guy, right? So what I'm going to do is I'm going to jointly solve this set of equations for QK plus 1 and VK plus 1. And like this guy, right, with the contact constraints. The message is, though, in terms of QK plus 1 and VK plus 1, this big fat equation is linear, right? So VK plus 1 shows up here. I already know M of Q. That's a fixed matrix if I evaluate QK plus 1, right? So I can sort of solve this whole thing for QK plus 1, VK plus 1, and it's linear. That's why you do this. So it turns out if I use Euler integration, the dynamics stuff becomes linear which is not true of like the midpoint stuff we did, right? Like we had to solve that with Newton and it was not linear, right? And you had to iterate. The win here is I can do this I solve one linear system and I'm done, right? I don't have to iterate and do Newton. So roughly speaking, that's like a, 3x, 4x speed up maybe, because I only have to solve one linear system instead of 3 to do Newton, right? Okay, so there's that trick, but Euler integration bad, much worse than midpoint, et cetera, as we know from the beginning of the class. So we've done some linearizing. By the way, this is a very particular flavor of Euler integration. Remember we talked about forward Euler and backward Euler at the beginning of the class, and one like adds energy and one damps energy artificially. What's this thing? Can anyone tell what this is? Okay, so let's just look at the first equation. Is the first equation doing forward or backward? I'm a forward. I plug in QK and VK. I evaluate all the dynamics terms at QK, VK, right? And then I solve for VK plus 1. So that's forward. What's the kinematic equation now? Backward, right? Because I'm evaluating this guy at VK plus 1. I'm evaluating the velocity at the next time step and solve for QK plus 1. So this is like half-half. It's like a mixed half forward, half backward Euler. This is sometimes called semi-implicit Euler. So it's not explicit, right? Because in explicit Euler, I just evaluate the dynamics and I go. Here I have to solve a linear system, right? To get the next time step, but it's a linear system. So this is sometimes called semi-implicit Euler. It's half backward, half forward, a little weird. It has slightly better properties than forward Euler in terms of stability, but it's still a first order method. It's just a weird hacky thing. Anyway, fun fact. Okay, now this is the other thing we do. So the theme here is linearizing. We're trying to make things as linear as possible, make them cheaper to solve. The other big thing, which is of questionable value, is the first one, you linearize some stuff and you get Euler integration essentially, or you do Euler integration because it makes the problem linear. The other thing you're going to do, or the next thing, is you're going to linearize the interpenetration constraint also over a time step. So what we've got, right, is, so in our version, we had just this guy, and we set this guy, we enforce the constraint on phi qk plus 1 directly, right? What these methods do is they approximate phi qk plus 1 as phi at qk plus partial phi partial qk times HVK plus 1. So you see what you're doing there? Basically, I'm doing a first order Taylor expansion of phi at the next time step by basically plugging in, I'm evaluating at QK, I'm evaluating its Jacobian at QK, and then the delta QK is this guy, right? According to my backward Euler rule, right? So I'm evaluating QK plus 1 according to this like first order Taylor expansion in terms of velocity, blah, blah, blah. So now this is a linear constraint. That's why I did this, right? It's a linear constraint in terms of the decision variables of the problem, which are QK plus 1, VK plus 1, right? So I made this linear in VK plus 1. Cool. That's next thing. The next thing is I'm also going to linearize the friction cone. I'll show you what that looks like. Basically, what you do is you take the round cone and you segment it into a bunch of faces and turn it into a pyramid is kind of the most standard thing. And usually you take an inner approximation of that guy. So here's like the original, here's the surface contact point. I'm going to end up with something that kind of looks like this, like the standard thing that most people do is like a four-sided pyramid kind of deal. And I'm going to attempt to draw this 3D style, which is hard for me because I'm bad at this. Something like that. And then you've got like, so what this would be, right? The original round cone would have been sort of like this, where the corners of the pyramid sort of are on the original. So this is like an inner approximation. Most of these things use a four-sided pyramid. You can, in the math, you can add as many faces as you want. So I could make it an 8-sided approximation or a 16-sided approximation, which would get me closer and closer and closer to the round version. Basically, the round version is like the infinite facet limit of this approximation, right? So actually this looks like though in the math is I take 2 norm of this guy and it turns into this 4-sided version, at least you can write as a 1 norm instead of a 2 norm is basically all that happens. And that gets you this, inner approximation thing. So that's kind of cool. And then the way you write this down kind of numerically is the following. So I take, basically I'm going to introduce a new sort of 4-dimensional friction vector that I'll call D that's equal to the original B, like so. So I have this Jacobian thing in here, and then I have a 4-dimensional D. And then what do I call this thing? And I can write the whole thing down like, and then I have D positive. So, and this guy. So this is a trick for writing down the 1 norm in a way that's like basically a smooth and has a bunch of linear constraints. So does everyone see how this works? The vector of 1s is usually called E. So what this is doing is I want to evaluate the 1 norm of B. The way I do that is I write it in terms of this D guy instead, where so all the elements of D have to be positive. What this is doing is basically D1 is the positive part of B. D3 is the negative part of B, right? So like if B1 is positive, then I get B1 just takes on that value, and then D3 is 0. If B1 were negative, this guy would be 0, and this guy would have, the absolute value of whatever that was, right? Does that make sense? So all the elements of this guy are always positive, and sort of depending on the sign of the corresponding element of B, it goes in one or the other, right? According to this guy. Does that make sense? So basically, like the D's then, the reason I do this is now all these guys are positive. So if I sum them, I get the sum of the absolute values of B, which is equal to the 1 norm. Does that make sense to everybody? Cool. Okay, so that's the trick. I basically introduce a bigger vector, like that's twice as big as the original friction vector. That has to be positive. And then I like do this guy where I, add them up with mine alternating signs to get like the original friction, right? Okay, some things about this though. This is obviously an approximation. It turns out when I'm doing when I write down the maximum dissipation thing, when I'm sliding, this tends to do a very weird thing that you can actually notice if you pay careful attention in Bullet or one of these simulators. What tends to happen when I'm sliding? So remember, what that maximum dissipation thing tries to do is suck out the most kinetic energy. So it's going to push you towards the most extreme, surface on this cone thing as far out as it can. So what that tends to do is push the B into the corners. So even if the true velocity direction is like on the face, so like if I'm sliding, whatever in this direction, if that direction isn't lined up exactly with one of the corners, the friction is going to end up pegged in one of the corners, the closest corner, basically. So I end up with friction that pushes me sideways instead of directly opposing the velocity. So this like legit happens in all these simulators. There's weird quirks in all of them. If you like actually pay careful attention, if I slide a brick not perfectly aligned with like one of the X or Y axes or something like this, you'll see it drift sideways for no reason. And this is why. It's because it's pegged into one of the corners of this friction pyramid and giving you like fictitious component, sideways component of friction. Fun fact, these all have quirks. Okay, that's kind of what all these guys do. So basically Dart, Bullet, et cetera, they use this weird semi-implicit Euler integration, which makes the dynamics part linear. They linearize the sign distance function, and then they linearize the friction cone. So now everything's linear, which is always nice. And then at the end of the day, if you stack all this stuff up, it turns out that this whole problem with all this stuff kind of linearized has a special, fits into a, well, let me write this down. Okay, so now all of the pieces of the problem oh, and we're at time. So we're just about done. Are linear. That's cool. Except the complementarity stuff. So we have a bunch of linear stuff plus complementarity conditions, right? And it turns out that is a specific thing that people study and write solvers for, called a linear complementarity problem. So these are called LCPs. And basically people like, there's a bunch of people who've studied these and written like special solvers for these guys. The general form of an LCP looks like this. So you have like linear equation. Then you've got, kind of these complementarity type things where these guys all have to be positive, and then, X times Z Hadamard product, right? Kind of thing that we talked about before equals 0. Okay, cool. That's a linear complementarity problem. Fun aside, does this look familiar? I mean, it kind of should. This is complementarity things. What's the top equation look like though? If we remember like this whole complementarity thing, we're used to these showing up in the form of KKT conditions, right? Okay, so the top equation, if I think about these as KKT conditions and that top equation is like a linear equation, what optimization problem is this the KKT conditions for? Basically, the question is, the top thing then is the gradient of something, right? The gradient of some kind of Lagrangian, and it's linear. So what things give you a linear equation when you take the gradient? Quadratic, right? So it turns out that these are the KKT conditions for a QP. Caveat, these are almost, so this turns out is super closely related to a QP. This is just kind of a side. But there's sort of one difference. So with a QP, there's a special condition on the quadratic objective. What is that? Yeah. So for a QP, A here, which would be the Hessian in the QP, would have to be symmetric positive definite. LCPs relax that condition. So an LCP, every QP is an LCP. A QP corresponds to an LCP with a positive definite A there. But LCPs are more general. And on an LCP, I can have it in general a, whatever A matrix I want. So that's kind of the trick. Like these are basically a strictly more like every QP is an LCP. Not every LCP is a QP. In general, A can be a general matrix here. And so it can, roughly speaking, correspond to a non-convex QP. That's kind of basically what's going on. Okay. And there are nice fast solvers for these guys. So basically the reason people do this is there are nice like interior point methods, et cetera, for solving these LCPs. So if you linearize a bunch of crap in the problem statement, get it into the form of an LCP, now I can just use a path, an LCP solver. And this is what all the current simulators do, basically. And we are done for the day. Thanks. If anyone, I'll hang out. Okay. The end.